This material has been reproduced and communicated to you by or on behalf of the Australian National University, in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
Okay, hi everyone. Welcome to lecture 12. We've only got 36 lectures, so after this we're 1/3 through. This course is kind of a mixed bag of a lot of things. Like, it's all connected, but there is a lot of topics, so it's important that you try and keep up. Okay, so last lecture we were working on implicit to explicit definitions of sequences. So having an implicit sort of equation given by like something recursive and then change it to a sort of explicit formula. So we did arithmetic and geometric, and then we started mixing them kind of together, and we got to this example. So reinvesting maybe into a bank or something, and we're getting a rate of return. So in the example, we're getting 3%, but then we added in this extra term of the bank fees, so minus $10 every sort of year or month or something. And we're starting with $20,000. So we came up with this nice sort of recursive implicit definition. So the amount of money we have at n plus 1 years is equal to the rate of return times the previous one plus the amount that you're paying, so a negative $10. And then, of course, C0 is your initial amount of money. So in this example, we're going to more focus on the general thing rather than actually substituting the values in until the end, just so we get an idea of what something like this will look like. So we start generating the sequence values. And so C0, of course, is C1, is C. C1 is R times C0 plus D. C2, just keep doing the same thing, substitute C1 in and simplify. Do C3 and simplify. And so you can notice that we're getting this sort of recursive pattern. So for C2, you notice there's an R squared times C. For C3, there's an R cubed times C. So the R is going up by 1. And then you notice that the second sort of part of the sum is R plus 1, and then it's R squared plus R plus 1. And so then the next term's probably going to be something like R cubed plus R squared plus R plus 1. So we're going to make a guess that Cn is going to look like something like this. So Cn is equal to R to the power of n times the initial value plus all of these terms times D. And then, so this is still a guess, and so we're going to claim using our geometric series formula. So we're just going to sum all of these up using our formula, and we get this. And then what you need to do is prove by mathematical induction that this is the same as this. And so the process is completely the same. You would start with the base case, check that that works, make the induction hypothesis that it's true for all values up to some n, and then check n plus 1 works. So yeah, maybe try this as an example. I'm sure in your workshops you're going to get to do some more induction as well. Okay, and so maybe we can work out how this formula is going when we actually substitute values in. After 10 years, we get this return by just substituting in our values, so R, C, R, 10, and so on. And so you'll notice that this was our original value when we did it without taking away these $10. And then once we started adding in this -10, we've actually lost $114.64. So that's more than 100, which is like the amount that you've removed each year. It's more to do with the fact that you're losing some of the interest in the following years. And so that's what I've just explained there. Okay, so with these mixed types of sequences of mixed geometric and arithmetic, then we have these sort of general formulas. So if you get an implicit definition and you have this sort of initial value, which is the first term, equal to A, and then you have this recursive formula that an plus 1 is equal to ran plus d for all n greater than k, then with this, you can prove by induction that you can get this explicit formula over here. And so just as a side note, this r not equal to 1 is the multiplier and d is the offset. And I guess the thing to notice here is this is just the sort of the geometric component, and then this is a sum, so it's a geometric series sum. That's all that's happening there. Okay, so let's just work through an example if I just give you the numbers. So if we have a mixed geometric arithmetic sequence with a multiplier, so our r is equal to 1/2, our offset is 2, and our first term is 1. What is the 10th term? Then we're just going to substitute these values into our formula. Since k equals 1, then 1. We put a 1 here and a 1 here, and then we just substitute n equals 10 into the formula. So nothing too tricky going on. And so maybe something you can observe, that since the multiplier is some sort of fractional number, this, as the years go on, this sequence is going to approach closer and closer to 4. And in fact, if you start at 4, then it's just going to stay on 4 the whole time. And so we call this a steady state. We're probably going to see this a little bit more in the Markov processes when we introduce matrices and stuff. These steady state vectors and stuff will appear. Cool. So that shows you how you can go from implicit definitions of geometric mixed with arithmetic sequences to get an explicit formula. Okay, so now we're going to play this sort of game. We're going to count moves. So some of you might have seen this game before, and we're going to use what we've previously worked on, this explicit formula, to solve how many moves it would take if we, say, had n rings here. Okay, so I'll describe the game. So it's called the Towers of Hanoi, and you have 3 pegs, 1, 2, 3, and you have some number of punctured discs. And so you put them on the first peg here in an order so that the biggest one's on the bottom, and they get smaller and smaller as you go up. And the game is transfer all the discs here to the rightmost peg, so number 3 over here, but you have to abide by some specific rules. You can only move 1 disc at a time, and it has to be moved to one of the other discs because, well, moving it to one of the other pegs, because moving it to the same peg's kind of just wasting your time. And then you can only move discs that are at the top of one of the piles. Yep, so you can only move this disc. You can't say, pick them up, take one out and put it over. And then the final rule will be, no disc may sit on top of a smaller disc. So I couldn't take this small one, put it here, then take the bigger one and stick it on top. And so the overall problem that we're going to solve is, if we did 1 move per second, how fast or how long would it take to solve a puzzle with 64 discs? So we're going to assume without the number n equals 64 to start with. We'll just start with n discs, and we'll look at some of the first examples. And we're going to let xn be the number of moves or seconds required to solve the problem. Okay, so if we have 1 disc, it's pretty straightforward. We have our 1 disc, and we can move it straight away to peg 3. So that's 1 move. if we have two disks, then obviously you move this one to the second, and then you move the bottom one to the third, and then you move this one that's here now over to here. So that's going to take 3 moves. Okay. And now, so if you want to set up some sort of implicit formula, you're going to need to say, you're going to need to come up with a formula that's based on how many steps it takes for, say, the previous number n, and then apply that to work out what n plus 1 will be. So this is what we do here. So we want to move n plus 1 disks. The first thing you want to do is actually move the top n disks over, and instead of to say this one here, you want to move them in a way so that you solve the problem, but only by moving them to the second peg. And then, so what you do is then you just move, of course, this one over here, and then you're going to take all of these, and with how many moves it takes to move all of those to here using your rules, then you've worked out the problem, because it's going to be xn, and then plus 1, and then xn again. So that's what I've just described here. So you've got your n plus 1 disks, however many moves it takes to move the xn disks in the right way to peg 2, that's xn. Then you move this biggest disk over to the number 3, and then finally you do the same thing on this xn pile here of n disks, and move them over to there. So it's going to be xn plus 1 plus xn. So you can see we've set up a recursive formula. So we have this sort of implicit definition, and it's exactly the ones we've just discussed. So we've got a mixed geometric arithmetic sequence with multiplier 2, offset 1, and first term 1. And so then we can just use our explicit formula and work out how many moves it's going to take. And it actually simplifies to something pretty nice. So if you've got n disks, it's going to take 2 to the power of n minus 1 moves. And so if you saw this number, you'd be pretty concerned, because if we want to do 64, then 2 to the power of 64 is an outrageously big number. So if we wanted to solve this problem and we could only do 1 move per second, then we've got 5.8 times 10 to the 11 years to solve the problem, which is, I think, older than the universe. So these problems can get quickly out of hand if you get something that's kind of exponential on the number of things you've got. Does anyone have any questions about this? It's a pretty neat solution. And it leads well into the next topic, because we're going to go through sorting. And sorting's kind of based on this idea of it's a good algorithm if it doesn't take many moves to do. Okay, so we'll move on to sorting. And so first I need to tell you what a sorting algorithm is, and then we're going to go through, in this lecture, we're going to go through one algorithm which can sort something, and then the next lecture we're going to go through probably a better sort of algorithm. Okay. So let n be some number and s be a set, and we're just going to take a sequence which is indexed by this set n, so 1 up to n, and it's a sequence where the elements are inside this set. And just as a reminder, sequences, they can have the same element multiple times. So you might have S being maybe the alphabet, and so the letter B might appear 3 times in this. So what is the sorting algorithm? A sorting algorithm is a procedure, and it sorts a sequence into an increasing order according to some specified ordering rules. So it might be something like sorted into smallest number to biggest number, or biggest number to smallest number. alphabetical order, or something else. So what this means kind of mathematically is we start with this sequence, and then we're going to do a rearrangement on this sequence so that these are all in an increasing order, where this less than or equals to denotes some ordering rule, and it's going to be some sort of total ordering rule. So if you remember from our equivalence relations, this kind of needs to be a total order so that you can compare all of these elements. So just some basic examples. If you've got a list sequence where the sequence is just these 5 names, so Jane, Fred, Joe, Jane, and Anne, then we want to sort the algorithm into alphabetical order. So alphabetical order is going to be our sort of ordering rule. Then the sorting algorithm will output Anne, Fred, Jane, Jane, Joe. So that's kind of just the purpose of what sorting algorithms do. We're going to have to introduce a fair bit of notation to work with sorting algorithms, so bear with me a little bit. So the first thing we've got is an index set, and so it's going to be some set of the non-negative numbers, and it's going to be some finite set. We don't want to be indexing over and trying to sort an infinite set or anything like that. So I is just the numbers between S and F. And we're going to call S the start index and F the finish index. So if we have I 3, 4, 5, 6, then S is 3 and F is 6. So sometimes we're going to denote things a little bit differently. So if we've got our index set and we have this sequence, then we might just write it simply like this, because we know we're working over natural numbers, so everything's a little bit simpler. So just S dot dot F. So suppose we've got this formula here. So AN's our sequence. These A's are going to be our sequence, and we're going to take a sequence from 3 to 6. And so our outputs from this sequence is going to be 7, 9, 11, and 13. Okay, and then so when you're sorting something, what you're doing is you're permuting, and so it's going to be some sort of function, and it's going to be a bijection because you're sending this index set to another index set. So an index permutation on an index set I is a bijection from I to I. And so we're going to have some special notation for these index permutations. So if we've got an index set S to F, then we can specify this permutation with this notation here. So pi is a function, and this notation just means S is getting sent to pi S, S plus 1 is getting sent to pi S plus 1, F is getting sent to pi F. And it's really important that the function is bijective, otherwise it's not a permutation, because it might be sending 2 objects to the same object, which isn't good. And so here's just a simple example on our index set we've defined before. So pi equals this thing here, and all that means is pi 3 is equal to 6, pi 4 is equal to 4, pi 5 is equal to 3, and pi 6 is equal to 5. So the whole point of these index permutations is, well, you're going to be writing loops, and the index is going to be changing, and you don't want to be, playing around with the objects themselves when you're moving around. It's easier just to work with the numbers. So it allows for a more precise algorithm specification. And then, depending on what you're ordering, maybe moving around, if you're ordering, say, you've got a list of programs or something, you don't want to move them around in the computer because they're big, and so it's hard to move them around. So give them indexing, and then you're just moving the index around. And so what our sorting algorithm's actually doing is just telling us how we would rearrange things, not actually rearranging them. Okay. A reordering of a sequence is a sequence yn such that yn is equal to x pi n for some index permutation pi. So we apply our permutation to our index set and then look at what the sequence changes. And so when you're doing these algorithms, you're actually not probably going to do an actual reordering of these, but yeah, you still need to know what it's called. So for example, with our previous example, we've got this permutation, we've got our sequence, and then our reordered sequence, according to this permutation, is, well, 3 is going to go to 6, and so 3 was associated to 7. Wait a second, I've got myself confused. Yeah. So 3 is going to 6, which is, so A3 is this one here, but A pi of 3 is going to be A6, and A6 is this one here, so it's 13. Yeah. And so just another example here that we did before, we can names, I think this might be just a typo, sorry. So we've got our sequence, Jane, Fred, Joe, Jane, and Anne, and we have our permutation where things are, our index set is this. Yeah, so this is the reordering that we've done, and I'm just showing you what the permutation is. Yeah, sorry. Does anyone have too many questions about this? Sorry, I kind of got myself confused. So all we did before is we just rearranged this directly into the ordered set, and all I'm trying to say here is when we're reordering things, we don't actually reorder the set, we just define the permutation that would reorder this set. So Jane is in position 1, but we see that Jane was moving to position 5, so of course the permutation is 1 to 5. Fred was in position 2. Fred ends up still in position 2, so the permutation is 2 to 2. Okay, so the first step, we're going to do the selection sort algorithm, but before that we need to at least be able to work out what the least element in the sequence is going to be. So I'm going to introduce the least element algorithm with an example, then we'll go through the pseudocode and we'll apply the pseudocode to another example. So this isn't a sorting algorithm, it's just working out what the least element of the algorithm is and then reordering it in some way, the sequence that you have, or at least reordering the index. Okay, so let's look at an example. This should be a 3. So we've got our sequence, which is JOE, with index set 1, 2, 3. Our index function, so our permutation, is beginning as just, it sends the element pi 1 to 1, pi 2 to 2, pi 3 to 3. So it's just like fixing this JOE in the same position. And then we're going to find a modification to this, which puts the least sort of alphabetical element at the beginning. So what we do is we begin with our marker M. And so what our marker M is going to be is it's the least element in the sequence that we've tested so far. So we start with M equals 1, and then maybe it's going to change as we move along. And then we start our index that we're going to be considering, so comparing M2. So we're comparing M equals 1 to this index, this element given by the index I equals 2. So we compare x1 and j, x1 equal to j and x2 equal to O. And since j is before O in our alphabet, so we're using the order on the alphabet, we keep M stuck at 1 as our marker. We don't change it because it's still the least in the sequence we've tested so far. And then we increase the sort of the comparing index by 1. So we change I to 2 plus 1, which is 3. So then we compare our marker, so m equals 1, still m equals 1, and we compare it to the index comparison. So we compare it to I equals 3, so J and E. Since E is before J in the alphabet, we change our marker to M equals 3. So now E is the sort of the least, alphabetically speaking, element of this sequence that we've tested. And then, since we can't increase our index anymore, we will stop the algorithm. And after we've done that, our output is this marker. And what we do is we change our permutation by switching our marker with the first element of the index set. So we've changed pi 1 from going to 1. We're changing it to 3 because that's the position that E was in. Pi 2 stays the same, and then pi 3 is switching with the 1, so pi 3 is now 1. Does that kind of make sense? Yep, cool. So this is just an example of how it works. I've talked about it. Now we're actually going to go through the pseudocode so that it's a little bit clearer when you're applying it to different cases. So when we write an algorithm, just some notation, we're going to write A with this left arrow B to mean we assign A with the value B, and we're not changing B in any way. So sometimes people will write this as define A equals to B. So when we apply this least element algorithm, we're going to start with a sequence, so xi, indexed by S to F, and our elements of this sequence are going to be inside some set S. And on this set S, we have some nice ordering rule, which gives us a total ordering, and our index function pi is going to be on this index set here. Yep. And so when we begin, our index function is just going to be the identity index function, so it's going to send S to S, and so on. And the output we want is a modification to pi. So our permutation, so that x pi s is less than or equal to x pi I for all I in S to F. So all we're saying here is that our start index is, we're going to move the least value, we're going to move the index that's associated to the least element in S so that it's at the beginning. So that's all I've done before in the previous example. Okay. So our method is that we're going to initiate by defining I to be S plus 1. So I is going to be our sort of comparing index. And we're going to set M as our marker. So this is the least sequence member so far tested. Well, x pi m is the least sequence member so far tested. So we're going to set this to S. So that's the first element so far. Okay, so now we define a loop, and the first thing you do when you define a loop is make sure that it's going to stop at some point. And the obvious place to stop is when our comparing index gets outside of our indexing set range. So as soon as I gets to f plus 1, then we're going to stop. Then we've got this step that we've looked at before. If our x pi I is strictly less than x pi m, so we're removing the case where it's possibly equal, then we're going to replace our marker with this I. And all we're saying now is the element that is the least in our sequence that we've tested so far is now I. And then we move on to the next element in the indexing set. So we change I to I plus 1. And then we repeat the loop. So this is exactly what I went through on the previous slide, but it's just written in pseudocode, and like maybe the abstraction is difficult to get your head around, but if you work through it and compare it to examples, then it should be okay. Okay, and so after we've finished repeating the loop, at the end, we take our marker and we're going to swap the value of pi s and the value of pi m. So we're not actually moving the xi's around, we're just moving the index set around. And all we've done is we've made our least element go into the start position and switched the starting position with that other one. Okay, so let's do another example, a little bit different, and we'll just go through the code to see how it works. So our indexing set's going to be 1 to 6. Our permutation at the beginning is just 1, 2, 3, 4, 5, 6, so not changing anything. And our sequence that we're defining is going to be F, D, C, E, B, C. And we're going to take the order to be the alphabetical order again. And so maybe I'll ask in like the workshops or quizzes or something to trace an algorithm. All that means is to go through the algorithm and apply it to this example and like give all the details of how it works. So what's our I? Our I is s plus 1, so that's 2. Our m, we're starting at s, so that's 1. So our I is 2 and our m is 1. What's x pi I? That's exactly the value in the second. X pi 2 is exactly this one here. X pi m is the first one. Which ones are smaller? Obviously D is before in the alphabet. So that means we're going to change m to the I that we've just compared it to. So we change m to 2. And then we move I from 2 up 1 to 3. And then we do the same process. So what's x pi 3? X pi 3 is exactly C. And then x pi 2 is, of course, the D that we've just found. C comes before D. So again, we change our marker according to this. And so our M will become 3, and then we just increase our index by 1 to 4. And then I guess the next one is a little bit more interesting because we don't do any changing. So when I is equal to 4, we get x pi 4 is E, and then x pi of 3 is C. C is before E, and so we don't make this change of changing the marker. C is still the least element that we've checked. So the index goes up by 1, but our marker doesn't change. And then you just continue on. And of course, what happens at the end is we find that B is our least element. And what position was that in? That was in position 5. So our marker at the end is going to come out as 5. And so then you write down what the actual modification to pi is going to be. Everything stays the same when you do this least element algorithm, other than we're going to switch the 5 and the 1. Cool. Does anyone have any questions about this algorithm? I guess the point of this is like, it's very easy to sit down and stare at something and go, oh yeah, that's the least one, just move it to the front. But like when you try to put it into a computer, it's a little more challenging. But if you actually code something up like this, then you can apply it to general cases as opposed to just doing it for specific examples. Okay, so what we're going to do is we're going to use this least element algorithm to do a sorting. And the sorting method we're going to use is the selection sort algorithm. So this is kind of the most, well, it's the one that you'd probably think of first when you're doing a sorting algorithm, is the way I put it. So let's continue on with our example. So I've got our sequence Joe with index set 1, 2, 3. Our index function begins with it being just the identity permutation, so it fixes each of the index elements. And our aim now is to rearrange Joe into alphabetical order. So what we're going to do is we're going to apply the least element algorithm. I shouldn't write 1, 2, 3. I should write to the actual sequence that we've written. So we're going to apply this least element algorithm that we've done before, and this gives us a modification to pi given by pi1 equal to 3, pi2 equal to 2, and pi3 equal to 3. So all I've done is I've noticed that E is the smallest in terms of alphabetical order, and I've put it to the front and moved the J to where the E was. Okay. Then the next step is you apply this least element algorithm again, but what we've done is we're only considering the index set 2, 3. So we're kind of ignoring this one here. And when you apply this, so what you're doing, and you'll notice that we're actually doing this permutation on the sequence X inside. So this E has now been put at the front and is fixed there, and then we're looking at the new sort of thing, which would be something that looks like OJ is our kind of new sequence that we're looking at. But we're not really looking at this, we're just tracking it with our permutation set. And so if we apply this algorithm again, we gain a modification to pi given by this. So our pi3 is staying the same because we've already fixed that one, and then because O is after J, we're going to do a switch of those. So pi1 is going to go to 2, and pi2 is going to go to 3. We stop this algorithm since we've reached the end of our indexing. I don't think this word should be here. And that's how the selection sort algorithm works in an example. And now we'll work through sort of the pseudocode. And the pseudocode in this case is a little bit easier, I think, because we've set up this least element algorithm nicely. So our input is going to be our sequence with our ordering rule, and we're going to have an index function pi, and it starts as just mapping things to themselves. And then our output is going to be a modification to pi, so changing this permutation so that everything is in a nice increasing order after we apply pi to the indexes. Okay, so what's the method? We're going to start with our s equal to 1, and then we're going to run a loop. So if s is equal to n, then we're going to stop, because once you're at the end, you don't have this thing to compare to the next thing, so we stop there. Then we run the least element algorithm on our sequence that we've got, and you'll notice that we're applying it. We've got our pi applied. So we're not writing xi's here because we're going to be running a loop, and so the pi is going to be changing. So we need to make sure that this works. Okay, and so we run our least element algorithm. We find the least element, and we move that to the front with our pi, and then we're going to change s to s plus 1. So we're going to move one more step. And so what you'll notice is that that will mean that we're no longer considering this first element in the algorithm. We're only considering the next part, and then we do the least element algorithm again, and we move one to the front, and then we move it a little bit more. So let's do an example, because I think examples are much, much clearer. So we're going to start with this example that we did with the least element algorithm. So we've got our input where n is 6, our index set is 1 to 6, our starting pi is going to be 1, 2, 3, 4, 5, 6. And then after the first iteration, what we found out using the least element algorithm is that the 1 is going to get switched with the 5 because b is in that position, it's the least element. So after the first iteration, when s is equal to 1, we're going to get an output of pi looking like this. Then we rerun over the loop, and since s is equal to 2, we only need to consider kind of this part here. We look at this part here and we go, which element is the least? The least element is this one and this one, but the algorithm that we've defined kind of chooses this one first. And so we're going to switch the 2 and the 3. So that's what's happened here. Repeat again. The next least element is the 6. So we're going to switch our D with the 6, with the C. And then you repeat it again, and so on, until you get to the end of our sum. So until s is equal to n, which in this case is 6. Okay, and so again, I just really want to highlight that this is sort of doing the trace of this algorithm we've defined here, and the output is not the rearranged sequence, it's the permutation of the sequence. So, yeah, we have time, that's good. So we want to understand whether our selection sort algorithm works well or not, and the way usually you would measure if a sorting algorithm is good is how many comparisons you have to do, because all the other parts in the code that we're doing are very simple, like we're just adding one or switching things around. So those are all easy to do computationally, but the actual comparisons might be tricky to do. So that's the thing we're going to measure. Yeah, so how many comparisons do we have to do? How many times do we need to check that something is less than something or not? So let's go through our selection sort algorithm. You'll notice that it happens n-1 times, because you just need to apply this sort of least element algorithm n-1 times. And so you do it once for s equals 1 up to n-1. And then the least element algorithm uses n minus s comparisons. So if you've got, say, n elements and you do the least element algorithm, then you're comparing this one with this one, this one with this one, this one. So that's how it works. So the first iteration will do n-1 comparisons. The second iteration does n-2 comparisons, and so on. So the last iteration, you do one comparison. So you can see how this kind of links up with what we did before with these different sequences and how we can find their sums. So we've got a total number of comparisons, Tn, given by this sum here, which is just 1 plus 2 plus up to n-1. This is an arithmetic series, and the way that you calculate it is you take the number of terms divided by 2, and number of terms times the average of the terms. The average of the first term and the last term, I should say. Yeah. So if we simplify that, then we get this nice formula here for the number of operations that we've done to do the selection sort algorithm. And I guess maybe something to notice here is this is kind of like some sort of parabola going on. So it's definitely increasing more and more as we move along. It's not something like exponential increasing, but it's still not great. So just to end, I'm going to go through what we're kind of going to do the next lecture. So there are other sort of sorting algorithms. The ones that you choose might depend on the data set that you've got. Maybe you know something very special about the data set that you've got, like after some number over 100, you know the next one's going to be a tiny number for some reason, just because of how the data works. Then maybe there's a better sorting algorithm to use because of that. So you can design your own algorithms depending on the data structure you've got. And so if you're going to learn more about sorting algorithms, then probably the course that you'd have to look to is something on algorithms and data structures. So the next algorithm that we'll look at next week is merge sort, which is maybe a little bit trickier. It's not the first thing you would think of when you're ordering something, but it turns out it's much more efficient, a lot less steps. So that's a good reason to use it instead. And so, yeah, we'll get a chance to compare the two algorithms and discuss their advantages and disadvantages. And so I believe in the next lecture, I will not be indexing the function pi just to keep things a little bit simpler. But like when you're doing it properly, it's probably preferable that you do the indexing so you're not moving the actual objects around too much. And so again, with merge sort, there's going to be this extra sub-algorithm that's going to be different to the least element algorithm. And so we're going to have to treat that first. Cool. So that's it for today. Let me know if you have any questions.